propagating. Okay. Understand? So whenever you have a crack here, you provide a reinforcement to prevent it from opening up. Okay. All right. So that is why we need this torsional shear link. And because we also have the cracks on top, so we will have a closed shear link. Okay, so if you look at the cross section, first we have the torsional shear link. We have to provide this. Okay, we have to provide this. So and the shear link will be in a link, okay, and it's going to be, let's say for example, the result would be, let's say T12 at 200 spacing or T16 at 150 spacing. See what I'm saying? Okay. So first, our end result would be what is the size you are going to use for the shear link. Okay, it could be T10, could be T12, T16, and so forth, right? Let's just say we have T10, right? Then you ask yourself, okay, I'm going to use T10, so what's the spacing that I need to provide? Okay, is it 100, 200, 300? How much is sufficient? Okay, so the design would be, let's say T10 at 200 or T10 at 150. So how do we get this result from this equation? Let's say this equation here, our design equation. So now here is B, design for torsional shear link. Okay. Our design equation is this one, ASV over SV is equal to T divided by 0.8 x1 y1 and 0.95 x of yv. Okay. Okay. Now this one is ASV is what? ASV is the shear link area. Okay. This ASV is equal to total shear link area. And SV is equal to shear link spacing. Okay, understand? Okay, so this is the shear link area per unit spacing. Okay, is calculated based on this T divided by 0.8 x1 y1, 0.95 f of yv. Okay. Now in this case, T will be 50 kilonewton meter. Okay, all right, 0.8. So the question is, what is x1 and y1? Okay, this one here is 300, and over here is 500. Okay, all right. This dimension here is x1. Okay, this is the shear link, right? This is a shear link. So the shear link is a rectangular shape, so it has a short dimension and a long dimension, right? So the shear link, the short dimension is x1. The long dimension is y1. Okay, in the okay, if you look at this problem here, this is x1. I've given in the final exam. I also give you the x1 and the y1. How do you calculate? For example, here, because this beam here is 550 and 375. Okay, so the y1 would be this one, the bigger dimension. X1 will be shorter dimension. Okay, so y1, how do we calculate it? Is equal to 550 minus the cover and minus the bar diameter. So that's why I say minus both sides and give you 460. Okay, but in the that's how x1 and y1 are calculated. So that means your y1 you base on h max, right? Subtract the cover, subtract the bar diameter, will give you y1. Okay, but in the exam I calculate it for you. You just use x1, y1. Understand what I'm saying? All right. So here in this case, let's say is 550, right? So here is x1 I say 210. Okay, all right, and then y1 is 460. Okay, understand? Yeah. Okay. In other words, this one is equal to 300 minus 90, minus the both side cover and the rebar end. And this one is 550 minus 90. Okay, alright, that's how it comes about. And here is 0.95 F sub YV. So in the British code, there are two types of the steel. Here I give you the FYV is 460. FYV 460. And I also give you the FC, the cube strength is 30 MPa, right? Okay. Alright. So here is 0.95, 460 MPa. Okay. Alright. So this is millimeter, and so forth, right? Okay. Now, and this is equal to Newton per millimeter square, right? So now I need to convert this to Newton millimeter, right? Again, same thing. Here I need to 50 times 10 to the 6 Newton millimeter. Okay? Yeah. So what is this value here? Here we have 0.8 multiplied by 210 multiplied by 460 multiplied by 0.95 and 460, right? And then here I have Newton. Okay? Because millimeter square, so divided. So becomes Newton. Okay? Alright. So what is this one? 0.8 multiplied by 210 multiplied by 460 multiplied by 0.95, 460. What's the value?
1.48
Times 10 to the cube.
Newton millimeter.
Huh? Okay. You just multiply this one first.
Uh, 33.7 times 10 power of 6.
Huh?
33.7 times 10 power of 6.
23.7.
33.
22.
33.
32.
33.
33.7.
Yes.
Right?
Yeah.
Times 10 to the 6 Newton, right? And here 50 times 10 to the 6 Newton millimeter, right? Okay, then this thing cancel out, right? And what you have is 50 divided by 33.7. Okay, alright. Now I want you to notice that this one, 50. This one 50 kilonewton meter. You just write 50 times 10 to the 6 Newton millimeter. Okay, because this one eventually will get cancelled. Okay, understand? Alright. So now, what's the units? Newton. Just millimeter, right?
Yeah.
Just millimeter. Actually, this unit here is millimeter square per millimeter. Because this is ASP or SP. ASP is millimeter square. Spacing is millimeter. Understand? So what is this telling me is that means 1 millimeter spacing, I need 1.48 millimeter square of area, shearling area. Okay, shearling area. Okay, now how do I convert? This is the design value. How do I convert it to here? Question is this. Okay, now so normally I would ask you to, okay, we have two parameters, the size and the spacing. So normally we choose the size first and then find the spacing. Okay, you can choose T10, T12 or T8. Okay, because the size normally either for the length of 8, 10 or 12. Very seldom we go to T16, T25. Okay, normally is 8, 10 or 12. Commonly used is T10. Let's say we use T10, right? So let's say this is T10. This is T10. The ASB is this leg, both legs. Okay, it's both legs, not just one leg. Okay, the one leg for T10, the one leg is 78.4 millimeter square. Okay, so one leg is, so when you do both legs, okay, is 78.4. So ASB is equal to 2 times 78.4 millimeter square. If you provide T10, that means I'm providing ASB equal to 2 times 78.4. Okay, understand now? Okay, look here. ASP, area of 2 legs of closed link at the section. Okay, not just one leg, 2 legs. Huh? Okay, so let me rewrite. T10, the area is equal to 78.4 millimeter square. So this is A10, area of T10. Okay, is equal to 78.4, meaning that ASB is equal to 2 times 78.4, 2 legs, millimeter square. So this is what? 78.4 multiplied by 2. 100 and
156.8.
156.8.